You know, we're all using these incredibly powerful AI models every day. But have you ever just stopped and wondered about the insane engineering it takes to make them fast enough to actually have a conversation with? Well, today, we're going to pull back the curtain on inference optimization. This is the hidden science of making AI not just smart, but actually practical.
You know that feeling, right? You ask a really complex question, and the AI just pauses. It feels like it's thinking. Well, that lag, that slowness, is honestly one of the biggest hurdles keeping AI from being everywhere in everything we do. So what is actually going on under the hood?
This quote just nails it. It really frames this entire conversation perfectly. Because the real bottleneck for AI right now isn't about raw intelligence. It's all about speed and cost. I mean, think about it. An AI that's a genius but takes a whole minute to answer you, that's just a cool novelty. But an AI that's instant and affordable, that is a revolution.
All right, so let's put on our engineering hats for a bit. We're going to break down the hard physical and, yep, the economic limits that really define what's even possible with AI today.
So engineers are basically fighting this war on three different fronts. They can tweak the AI model itself to make it more efficient, they can get way smarter about the physical hardware it's running on, and they can totally redesign the service that's delivering the AI's answers to millions of users. And we're going to touch on all three.
But hold on. Before we can make something faster, we kind of have to agree on what fast even means. And in the world of AI, it is not as simple as just starting a stopwatch. Nope, we need much more sophisticated ways to actually measure performance. Okay, so first things first, we have to split latency into two different pieces. First up is time to first token, or TTFT. That's that initial pause you feel, that thinking time before the AI even starts to respond. Then you've got time per output token, or TPOT. You can just think of this as the AI's typing speed. A really good user experience means you have to optimize for both of these. And this leads to a really crucial distinction. You've got throughput, which is just raw speed, how many tokens the system can possibly crank out per second. But then you have goodput, and that's the metric that really matters. That's how many of those tokens were part of a response that was actually useful and met what the user needed. You can have amazing throughput, but just awful goodput.
Okay, now for a big one. Let's bust a common myth. If you see a dashboard that says 100% GPU utilization, that does not mean the chip is working as hard as it can. Not even close. It could just be busy waiting around for data. The pros, they use smarter metrics. Things like MFU, or model flops utilization, which measures how efficiently the chip is actually doing math. And MBU, memory bandwidth utilization, which tells you how well it's moving data around. Those are the numbers that show you true productivity.
So now that we know how to actually measure the problem, let's dive into that first layer of solutions, making the AI model itself fundamentally more efficient.
So transformer models, that's the architecture behind things like ChatGPT, and deep inside them, there's this one specific component that uses up an absolutely monstrous amount of memory, and it creates this huge bottleneck. Any guesses what it is?
It's called the KV cache. And in simple terms, it's basically the model's short-term memory. As your conversation gets longer, the model stores all this key info in the cache so it doesn't have to reprocess the entire chat history for every single new word it generates. It's essential, but, oh boy, it has a massive downside.
And that downside is its size. For just one user who's having a long conversation with a pretty moderately sized model, that KV cache alone can eat up 54 gigabytes of precious memory. That is more RAM than most high-end gaming PCs have in total. Now just try to imagine serving millions of users at once. You see the problem?
Right, so we need some seriously clever ways to work around this bottleneck. One of the coolest tricks out there is called speculative decoding, and it's a really smart way to break out of that slow, one-word-at-a-time generation process.
So here's how it works. It's like a team-up. First, a small, super-fast draft model guesses a few words ahead. Then, the big, powerful model comes in and checks all of those guesses in one single, parallel step. It looks at the guesses, accepts the longest correct sequence, and bam. The result is that the model literally jumps forward, generating text in big chunks instead of slogging through one word at a time. It's brilliant.
Another absolutely vital technique is quantization. Honestly, the best analogy is just image compression. You take the model's ultra-precise, high-resolution numbers and you represent them with a little less precision, kind of like saving a JPEG. This dramatically shrinks the model's size and eases that memory pressure, and a lot of the time it has very little impact on the final quality.
Okay, fixing the model itself, that's a huge piece of the puzzle.
But it is only half the battle. You also have to be incredibly smart about how you deliver the AI's answers to potentially millions of users. And this, my friends, is the art of inference serving. So the most fundamental concept here is batching. Sending one user request at a time to a GPU is like calling a separate Uber for every single person leaving a concert. It's just wildly inefficient. Batching is the smart move. It groups all those requests together, fills up a bus, and makes every single trip way more cost-effective and productive.
But what if that bus never had to stop? What if it just kept going? Well, that's the genius idea behind continuous batching. The very instant one user's request is finished and they get off the bus, a new request that's been waiting in line immediately hops on. This just maximizes efficiency, and it keeps those super expensive GPUs working productively all the time.
Okay, now for a more advanced problem. The AI's job really has two very different parts. The prefill phase is when it first reads your prompt. This is super compute-intensive, lots of math. Then there's the decode phase where it generates the answer word by word, and that is very memory-intensive. Trying to do both on the same hardware creates a massive traffic jam. It's like having race cars and heavy-duty trucks trying to share the same single-lane road.
The solution? It's actually incredibly elegant. You just give them separate lanes. You decouple them. Many of the top-tier AI systems now run the prefill and decode phases on completely different machines, where each one is specialized for its specific task. This disaggregation, this decoupling, it solves the traffic jam and it dramatically improves the overall performance.
So let's bring this all together. What does this all mean? We've basically seen how engineers are fighting a war against latency on multiple fronts, from the model's deep inner code all the way up to the global systems that serve it to you.
So the key takeaways here are pretty clear, right? First, you have to measure what actually matters. Forget the vanity metrics and look at things like TTFT, goodput, and MFU. Second, you have to go in and attack the model's core bottlenecks, like that monster KV cache. And finally, you have to be unbelievably intelligent about managing your resources with tricks like continuous batching and decoupling.
And that brings us right back to the core idea of this whole thing. We are so often dazzled by what an AI can do that it's really easy to forget the incredible unsung engineering that makes it possible in the first place. The real magic isn't just the AI's intelligence, it's the speed and the accessibility that turns that intelligence into a useful, real-world tool for everybody.
But this leaves us with one final fascinating question. AI models are only getting bigger and smarter and more complex. It's basically an ongoing arms race between the growing demands of these models and the pure ingenuity of the engineers who are trying to tame them. Will clever optimization always be enough to keep up? Well, that is something to think about.